next type of substituent that I'd like to take a look at with you is the deactivating meta-directing substituent. So typically what you're going to find in these cases is that the atom attached to the aromatic ring will have a partial positive charge on it or just a full positive charge. Electron density is going to be withdrawn inductively along that sigma bond, so the ring is less electron rich than benzene. And as a result of that, the molecules, for example, nitrobenzene here, it's about 100,000 times less reactive than benzene towards EAS type reactions. So recall, and this is something that we need to remember, we often write NO2 like this. But don't forget that it has a positive charge on that nitrogen. All right, so if we try to nitrate this, what we end up getting is our meta-substituted product being our major product. Yields are low for this, even though this is the major product. That doesn't mean we get great yields either, right? 100,000 times less reactive. Now that reactivity can be seen in looking, and the directing effect of that substituent can be seen by looking at the following diagram. So if we look at this, this is highlighting our ortho, our meta, and our para attack here. So if we look up here, and this is true of just of any EAS reaction, so we're going to use a generic electrophile here. If we add ortho, the problem is that we get this plus charge here adjacent to that positive charge. That's especially unstable, right? And then we get the other resonance structures here, and I'll let you put in the arrows and stuff. Now if you attack para, remember O and P often go together. So if we look down here below, right, here's your ortho, down here, here's your para. If you look down below here, you'll see that if we attack para, we get a plus charge here, and then we have one of those resonance structures generating a positive charge up at that carbon where the nitro group is attached. Again, that's not stable. So that resonance structure that's in red, along with the one up at the ortho, right, attack, that also, both of those are unstable. Whereas when we attack at meta, we have a plus, right, kind of to the left, across, and above. So in that situation, we simply avoid having adjacent positive charges next to each other. All right, so that's really important. Doesn't mean it's great at meta, it just means we avoid having those positive charges adjacent. Now, this will be true of any type of substituent that has a positive charge on it, or remember, a delta plus. So a lot of times we'll see delta pluses, and we see that in things like our carbonyl groups, for example. So a carbonyl group is going to have a delta plus here. So having the delta plus and the plus together is still not advantageous. It's a disadvantage to have this attack here. All right, so this is true also, we'll just make a note here, true also for the para, right? In the sense that you get those plus charges, the plus and the delta plus adjacent to each other, not good. Where the meta is going to end up having plus charges at positions that are not adjacent. So it's better to attack at the meta position. Now, putting all of that together, we can look at a little summary here. And it's pretty easy to remember these because all you really need to do is think of delta pluses. So what do we know? Well, we know the nitro group. We just talked about that one. That has a full plus on it. Sulfonic acids have oxygens that are going to make that sulfur have a delta plus on it. The cyano group gives us a delta plus here, right? Ketones and aldehydes, same deal. Esters, delta pluses. And then, of course, anything that has just a full positive charge also, like an NH3, would be true of that also, an ammonium salt. Now, up to this point, we've seen activating groups that are ortho-para-directing and deactivating groups that are meta-directing. Now, the last class is the exception to those first two rules, and that's halogens. So halogens are interesting because we know they're electronegative, and they are powerful electron withdrawing groups. So remember, electron withdrawing groups make molecules deactivated, right? So having full positive charge or partial positive charge on an atom that we're connected to pulls electron density away. So this does the same thing essentially, because we end up having a delta plus at these positions, right here. So that makes the ortho and the pair positions less nucleophilic, right? Now, the other thing that makes this a little different is that the halogens have lone pairs of electrons, so they can donate electron density through resonance if there's an adjacent positive charge. So let's look at this a little bit down below here. Here we have an example that I've written out for you guys for ortho. So remember, electrons being pulled away, that's what's making this deactivating. Here you have your electrophile adding at the ortho position. So that puts the plus charge adjacent here. So here we're adjacent to halogen. So that is good, right? So we want that because we get this additional resonance structure where you have a pi bond moving out of the ring. Right? So you get 4 resonance structures here. And the same kind of situation arises when we look at para. So when we have that positive charge adjacent to that lone pair, that's a favorable thing. We see that both in para and in ortho. Simply in meta, we don't see that additional resonance structure. So it's deactivating again because it's electron withdrawing, but it's OP directing because we have a lone pair bearing atom that can provide that additional resonance structure. Now down here below we have a little summary of our activators and deactivators and directors here. So over here on the left of our little line that I've highlighted as kind of being green over here, these are all going to be ortho para directing. So over here we're OP directing. The only thing that we have to watch out for is here, that's deactivating. So that's kind of the exception that we just talked about, right? Okay, and then coming over here to our right hand side, these are going to be meta directing, and most of the time they are also deactivating too, right? So we're looking at deactivating groups there.